So imagine that we have this kind of data, right? You see this kind of data. So here, let's say we plot the data with respect to house size, right? And this is the price. So the we are trying to predict price, and this is the how this is one of the parameters called house size. Okay, the data looks like this. Now, if you try to draw a straight line, you are underfitting or overfitting. This is underfitting. Why? Because it kind of is considering these two data points or maybe one or two data points. So it's like very simplistic model which we are trying to fit into the data. So generally in underfitting, we try to fit in a very simplistic model, such as we were trying to do um, addition in every kind of cases instead of shifting between the rest, right? So similarly here, we are trying to fit a very simplistic model into the data. All right. Now, the other end, this one, you see, it has kind of memorized every data points, you see, even though this data point might there might be an error, there might be a noise, there might be some misfunction in recording the data, but instead of considering that as an error, it has kind of figured out a graph, a polynomial degree of 100 uh, that fits into every data point. Okay, just like we memorize, right? So this graph kind of memorized every data point. Okay, now a proper model looks like this, you see. So it's okay to have a little bit error, but in case of complex models, you won't be able to figure this out by drawing a graph. But since we are able to visually see that this model has got lower error on the given data, as well as it kind of is able to show that the values are in kind of parabola. Okay, so visually we are able to figure out that yes, this one looks like it's fitting better. So this one is a proper model, this one is underfitting, and this one is overfitting. This is just to give you an idea how do you visualize the overfitting and underfitting. Okay, the extreme right, this one is the overfitting, this one is underfitting. Okay, now you can see that this is basically it's fitting every data point, it's memorizing every data point, and that's what is overfitting. All right, so this is how we can visualize the two things. So a higher degree polynomial strongly fits the housing prices data. It performs much better on training than the simple learning model. So you can see that every data point, if you give it, it'll be able to predict exactly same value, right? This might be looking to you like a hypothetical data, but it's very much true, as in you will see this very soon. Okay, if the training data is noisy, then the model is likely to detect patterns in the noise itself in an overfitting model, and these patterns will not generalize well. Okay, now another example is, let's say a complex model may detect a pattern like the fact that all countries in the training data with the W in their names have a life satisfaction as greater than 7. Okay, so let's say there is a model who has seen only few countries, say New Zealand, Norway, Sweden, and Switzerland, and it's trying to predict the it has come up with a theory like any name that has W in them, right? The life satisfaction is greater than 7, right? So in that case, the chance of it going wrong in the data that is it has not seen, for example, Rwanda and Zimbabwe, they also have W in the name, but their life satisfaction rule does not generalize well. Okay, so we will be tackling the overfitting, right? When you get stuck with underfitting, what you do, you come up with a better model, Like instead of drawing a straight line, we draw a parabola, right? In the same way, whenever we get stuck with underfitting, we make the model complex, we bring in better, and we bring in a better model, or we switch to say neural network or another complex model, right? um, Another thing that you will like to learn now is okay, so very quick, I want to give you this very quick idea, right? So underfitting is also called high bias, somebody on high bias, right? And the overfitting is called as variance. Overfitting, underfitting, and bias versus variance. Okay, so how about we loop through all possible models and figure out which fits well, and that's what we're going to do next. All right, good, very good. So let's say you have got a team of people in your room. Okay, all of you, please pay attention. This is a very interesting concept, and the team of people that who is in your room, right? Their problem is that they all have individuals have their own biases, right? Individuals have their own biases, right? Imagine that some of them have learned addition and subtraction along with multiplication. Some of them have not learned, let's say, one of them did not learn multiplication, other did not learn subtraction, other did not learn addition, and the fourth one did not learn the division. Okay, so there are, let's say, four people in a room, and all four people have their biases because they are not doing very great even on the test data, and they don't know it or they don't want to accept it. So there are four people in a room, all of them are underfitting. Okay, all of them are underfitting, and you have no other choice. You have no other choice than doing the exam using these four people. Yeah. So you have appeared in an exam, and you have these four people and you want to do really well in the exam, and you know that they might have their individual biases. Some might not know addition, some might not know division, some might not know multiplication, some might not know the addition, and so on, right? So basically you have got these four people in a room and you want to do well in exam. You don't have any other choice to go out. So of course the general way is we go out, try to run the model and so on. But right now you have got these three people, uh, four people, and fifth one is you, and you have no clue about anything about the maths at all. Okay, so you have got to utilize them. So what will you do? This point is track the performance of each one. Okay, let them go through paper individually, and we discuss and ask people to take ownership. Okay, 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 interesting. Okay, yes. So Manoj, and I'll say Deepak, Prashant, Robert, Robin, and Satyajit. Are you guys with me? It's a very interesting question. Question is that you have a paper to solve, and it's a maths paper which has all four kinds of questions, and you got four people to assist you because you have no clue about any of them, any of the questions, and now you want to utilize them. You do not know who is who, as in who knows what, and you also do not know that this particular question pertains to uh, is better with this person. Okay, you have no, it's a group of four and you do not know their individual expertise. Okay, one answer is that let's first figure out their expertise. But the other answer is that since we do not know and how much time it's going to take to figure out their expertise, the other one is ask one question to all four of them, right? Note down their answer. And as we said that if the question is related to say addition, only one of them does not know addition, right? So three of them are correct. So which means that if we do just random voting, if we let everyone vote, so the correct answers are going to get 3 votes, while the wrong answers are going to get 1 vote, right? You must have seen in then Who Wants to Be Millionaire, or in India also there is Kaun Banega Crorepati. In that, people go for the public vote, right? And similarly, we here go for voting on each question. We see the answer and then we take the one that got maximum vote. All right. And all the answers, if you notice, these are very good answers, and you will see that the variant of your answers when we talk about ensemble learning. Okay. So you will see that there is this whole mechanism of overcoming the underfitting by the way of ensembling them together is part of ensemble learning. Okay, so there are many techniques to learn the ensemble learning before we, because we wanted to be very clear that you can get the work done by the way of ensemble, and that's how most of the companies work, right? So as long as you have diverse set of people in a team and you are seeking their opinions and you ensemble them together, the chance of taking correct decisions is very right, very possible, right? If you have if you have all the people, let's say you have a team of people, right? And all of them don't like the people with, say, gray hair, okay? And you ask them to interview, you ask all of them to interview a person, and in case they all of them have the same bias, right? Exact same bias, you may not get great result by ensembling them. But if they are diverse, that somebody, one of them doesn't like gray hair, other doesn't like the blonde hair, other does not like the black hair, and so on. If they have different biases, you can get the work done. So in very simple thing, that before we jump ahead, I want to be clear that in case you are underfitting, in case there's a model that is underfitting, and you know that there are many ways to underfit, you can ensemble them and get the work done. Okay, so the dysenteries have been around for like 40 years, right? Have been maybe more than that. The dysenteries have been around. I mean, the theory is known for quite some time, and the dysenteries have been there for a really long time. The dysenteries were known for underfitting. Okay, and or you can say the dysenteries have been known for overfitting if we increase the depth and so on. So what we do is what somebody did in 2014, 3 years ago, that it ensembled the dysenteries, and meaning have lots of dysenteries, and get the uh, decisions based on the voting by individual model. And that's what has been winning the Kaggle competitions. It's called ensemble learning. Okay, so it's called XGBoost. XGBoost is nothing but the ensembled model of decision trees. Okay, so just I'm jumping ahead. So if you think about it, that right. So I'll just go back on one page. Okay, I hope I'm not. Okay, so I'm going to walk you through very simple thing. Okay, why the why what it means by underfitting. So here we talked about that this is underfitting, right? This is underfitting. Now imagine this for a moment, that there was one model which drew the line this way, right? The other drew the line a little bit. The first model only learned from first two data points, so it drew the line this way. The other one drew the line this way, right? The third model drew the line this way, somewhere like this. And fourth model drew the line this way. And fifth model drew the line this way. Okay, you see that? Now, there are one, two, three, four, five models out here. And right, and there could be more models, one joining this and this, right, joining this and this. Okay, so joining this and this, joining this and this. So there are so many different kind of models possible, right? But the important part is if you take the prediction of average their predictions, take the value of the outcome, average it out, the chances are you will get a very good model. Okay, the chances are you will get a very good model. So the important part is that you can convert an underfitting model into a proper model by ensembling them together. Okay, so even with the straight line fitting, you can actually do a very decent predictions. Okay, even with the straight line, you can do a very, I mean, the outcome that you'll see if you do like the way I'm describing, the chances are you will get this kind of model. Okay, was I able to explain to you, everyone? So as long as they are diverse, you can get a great outcome. So you can batch together a diverse underfitting model or in a group and get the work done. All right. This is an ensemble learning, and that's one of the reasons why people want diverse teams. Okay. If you have a model and it is underfitting, one thing is discard it in the favor of the one that is giving better results, right? Now, a number of times we realize that we don't have better model. We have just this model which is giving bad results. Okay. We've got just this model which is giving bad results and we don't have a better model, or we have hit the upper ceiling of getting the best model. Okay, so in that case, if we don't have a better model and we want better results, what we do is we we get such a kind of high a model which is high on bias, right? To have different diverse set of, we get the same algorithm but the model could be different. Like for example, this is a straight line, it's going from here, right? It's based on maybe this point and this point. We could draw a line based on this and this point, right? This and this point. So the model number one was like this. Model number two could be really high on bias like this. Model number three could be a straight line between these two data points, right? Model number three could be the straight line with these 2 points. So this is the fourth model, right? The fifth model could be basically based on this, right? This is, let's say, fifth model, correct? And so on. Now, what we could do is when we want to do prediction, we ask all of them. Okay, we ask the fifth line, hey, what will be the value at this point, at this point? So we'll say, okay, the value is going to be somewhere here, right? At this point, The value as per this first model is going to be somewhere here. Let's say we're trying to do that, right? So and so on. So you will see that when we average out their results, the outcome is going to be nearer to the actual. Okay, nearer to the actual when basically average out. This mechanism of converting an underfitting model into a proper model by combining multiple of them together, or multiple diverse models generated by the same algorithm together, or multiple algorithms together, is called the ensembling. Okay, uh, combining underfitting models to get great results is ensembling. Okay, the important part is that these ensemble model that we did, they should be diverse. They should not be exactly identical. Okay, if they all are identical, it's not very good outcome. Now, what we just showed you was something very important. You know what was so important? That the outcome of bringing together the people was better than the best. Okay, was better than the best. That's the important part. So out of these, let's say there's one line that's doing really good, but when the outcome of all the things together, like an average, then the outcome is more closer to the real. Question from Manojit, but finally we will use only one model or multiple? We'll use multiple in finally. Okay, because our purpose is to get the best results. Our purpose is not to worry about one model or multiple models. Okay, all right, so I think we are all ready, and we talked about the overfitting. Okay, so okay, so the other end, so to overcome underfitting, we choose better models, and or we basically ensemble them together if we can't have a better model. And in case of overfitting, force it, we force it to not memorize. Okay, we force it to not memorize. All right, so we tell it, hey, don't memorize, it's not necessary to memorize. And when you force it to not memorize, then you put constraint on it, on the model. Okay, we put constraint on the model, and we curtail its degree of freedom. Okay, we force it not to have too much variance. We basically do mathematical operations to curtail the degree of freedom of a complex model, so that it does not go haywire and fit everything. And that's basically how we tackle the overfitting. Consider a linear model. It has two parameters, theta 0 and theta 1. It gives the learning algorithm 2 degrees of freedom to adapt the model to the training data. It can either change the height or the slope of the line, right? Height of the height means the distance from the center when x is equals to 0, right? So that's basically the height we are talking about, and the slope. Slope is the angle. Now we have got two parameters. We could change both. Either we could change the height or we could change the slope, right? And we can fit the line. Now, if you're forced, if we force this algorithm to just, keep every line such that it goes through the center, right? We say that, hey, theta, first one is 0, which means the line must go through the center, and the algorithm or the model will have only 1 degree of freedom, that's changing the slope, right? So it'll allow, if we allow the algorithm to modify theta 1, which is the slope, it'll produce a simpler model than the 2 degree of freedom, but it'll be more complex than with just 1 degree of freedom. Okay, all right, so Okay, the second sentence is a bit wrong. So it'll produce a simple model with 2 degrees of simpler model than the. So if we have the outcome when we have modeled the outcome we are going to get is a proper line like theta 1 and theta 2 both it can tweak, right? But if we force it to draw the line through the center, it'll basically we are constraining it. We are constraining it, and it is having less degree of freedom, but it'll have less chances of overfitting. Okay, when we give less freedom, when we give less freedom to the model, right? Then it is okay. It's called regularization. When we are not giving an algorithm much freedom, okay, like in the last case when it went haywire, basically did not did not let go of any data points, then that it started overfitting. But if we force it not to have this much of freedom, then that's called constraining the model or regularizing the model. Okay, so if the model is overfitting, we regularize it or constrain it to not overfit. Okay, there are many techniques to do regularization so that so when we overcome underfitting, we end up with overfitting, right? That's a very common trend, and we basically, as a data scientist, we basically try to balance the two, right? It your model should not overfit and should not underfit. Okay, so here's an example of the dotted line represents the original model, right? And that was trained. This one was trained with few countries missing. This dashed line, you see this dashed line, model trained with all countries. This is trained with all countries. Okay. The solid line is a linear model trained with the same data as the first model, but regularization, right? You see this one. It's basically a linear model, this one, with the same data as the first model, yeah, but with the same, but with the regularization constraint. Okay, so so basically, if you see the, okay, we'll actually talk about it a little bit more later. Now, so essentially, all we are trying to say is that what we do is we regularize the models. We force them not to memorize too much, as by constraining the degree of freedom. And regularization forces the model to have a smaller slope, fits a bit less. This doesn't look. I mean, this doesn't convey too much. So we'll talk about it probably later. All right. So how do we choose the best model? When finding the best model, we'll have to find the right balance between fitting data perfectly and keeping the model simple enough to ensure that it'll generalize well. Okay, it should generalize well as it should, right, give great results. In simple words, it should give great results on the unseen data. Okay. A question from Robert is, how does this affect gradient descent? Okay, gradient descent, yes, a good question. So we are going to learn that part. Gradient descent is an optimizer algorithm. Instead of trying all possible lines, instead of all possible graph or line, what we do is we do a little bit of greediness. We basically see which going to which side is giving us better results, and we go to that side, and that's what is gradient descent in very simple words. So we're going to discuss that in detail, that how do we do regularization, and how do we observe the how do we when we are doing gradient descent, when we are doing this optimization, how do we uh, stop, where do we stop the gradient descent, that it does not start overfitting, and and so on. Okay, so we'll do that in more details. Okay, just be with me. So I'm going a little slow right now because this is the point where I'm letting these things settle with you about overfitting, underfitting, regularization, and so on. And we also talked about the ensembling. Okay, now moving ahead. Okay, underfitting is when the model is too simple to learn the underlying structure of data. Underfitting is often a result of excessively simple model. That's right. For example, a linear model of life satisfaction is prone to underfit because reality is just more complex than the model. So its predictions are bound to be inaccurate even on the training sample. Okay, so it happens. A question from Deepak is ML doesn't predict with 100% accuracy, not even 98% or 99. Then why do people use it for predictions and everybody wants 100% accuracy in predictions? Okay, so anybody wants to answer that question? Yes, it's an interesting question. Yeah. All right. So a quick answer to that is that we don't have alternatives. Okay. Like for example, even the human error is actually very high. And if the computer is giving better error on a particular task, I mean lesser error than the human, then you don't have any other choice. Okay. So that's why when we talked about the project, we said that we find out what is the current error. Okay. Because what happened was in the beginning, I so well remember that in long back at D Shaw, I mean, we were of the opinion that let's go with the models, like neural net kind of models long back. But a number of people were not open for it because one, it wasn't giving very accurate results. Second, it was not interpretable, meaning it was kind of black box and so on. So I very well remember this discussion in one of the teams that they said that no, we are okay with doing regression as opposed to going with a complex model. But that's a completely different argument. So right now, the answer is that we basically know how much accuracy is there currently with humans, with people. Therefore, if our model is giving better accuracy than that, we adopt it. Otherwise, we continue in our current model. All right. So good. All right. Okay. So yeah, how to solve the problem of underfitting? There is one more addition to be done by combining the underfitting models together in an ensemble, and that's also a very interesting way of overcoming underfitting. All right, let's train the model now. Let's get started. So this is how it's going to look like. So here we are using linear regression. It's basically this one. Okay, so we are going to go to my notebook. Where is the notebook? All right. I hope it has not. Yeah, it has been killed. Okay, I'm going to take it out. All right, so okay, it might take a bit of time to load this one. So all we're going to do is basically, all right. So here, so this is how we are going to do it. We are going to import the linear model, right? From the scikit-learn has a folder called linear model, which contains all the linear models, and one of them is linear regression. So we import linear regression, and linear regression is essentially drawing the line between all possible pair of uh, columns, or basically in all possible dimensions, and So we are saying linear regression equals linear regression, and we are initializing the algorithm, and then we are calling fit. Remember that we did fit earlier when we did when we did the scaling. So here fitting means generating the model. So since it's the same object, when we do fit, it's going to create the model in this object only. Okay, so here we are saying how linear regression dot fit. This is the left hand side, and this is the right hand side. This is the x, this is the y, this is the variable that we are trying to predict, and this is the data, the input data. All right. So as long as we are able to come up with this data as numbers, this data as numbers, it should be able to learn from it. So this is a supervised learning. So we already have labels with the value. Therefore, we are able to provide these labels, and we are saying that, right? So here we have the data of housing prepared, which has all the columns, the left-hand side one. These are independent variables, and this is a dependent variable. Okay, so here we go. And what will be the best way to run it? Okay, here we are, and what we'll do is we'll run everything above. Kernel, restart, no restarting, run all above. Okay, so we'll wait for this star to disappear, this asterisk to disappear. Okay, is it finished? I don't think so. There is a wait cursor. Okay, all right. So it's going to take a bit of time. So in the meantime, yes. Okay. So once we do that, once we run it, it will basically get this linear regression model, right? And we could just pick up one particular data point, like this one, okay? When we could just pick up this 5 records, right? We could just pick up the first 5 records from our actual data, and then, right? This is the data, this is the labels, and then we could transform this data that we are talking about, this data, using the same pipeline that we use to clean up this data, right? So we use the same pipeline to clean up this data, and we can do the predictions using this model that we have just generated. Okay, is the font clear to all of you? Okay, so let's run it. So we are here, right? So now let's run it. So you can see that these are the predictions. Okay, so it has done predictions on first 5 records. Okay, and we can also check the actual values. So these are the predictions, these are the actual values. Okay, now how do we know that these predictions are good? So what we do is we compute the mean squared error, right? There's a method called mean squared error in the module called matrix, sklearn matrices, and there we basically imported that, and on these 5 records, it's giving you this much error. Okay, this much error. Now let's do the same thing what we just did with linear regression. Okay, we will do the same thing with linear regression. So, with decision trees, we are importing decision tree. Decision tree is another model in which we cut the data into 2 parts, and we keep on doing so based on how close the data on either side is to each other. Okay, so basically that's what is decision tree. We'll go into more details. This is a dedicated chapter. Now, here, what we are doing is we are importing this entry, and that's the class, then initializing the object, and afterwards we are fitting it. Okay, fitting means training it. So this is the fit means training. We are training our model. This is a decent tree regressor on the on the given data. Now you can see that this training finished very quickly, right? Most of this training is finishing quickly because this data is not too big a deal for these models. Okay. Now the important part. Now do you see the error in case of dysentery? Here the error is how much? The error is 68,000. In case of dysentery, the the error is 0. What do you think is the problem? Please notice that we are testing it on first 5 records of this data. No, actually we are predicting on the same data here. Okay, so we are using the same data set to fit and predict, and the error we are getting is 0. What exactly seems to be the problem? Overfitting. Perfect. It's giving the overfitting. That's right. So it's a live example. We have purposefully done that. So you can see that the dysentery regressor is overfitting, right? Okay. You could do exactly same thing with the linear model as well. Okay. So let's say this. Okay. Housing predictions. We call it linear regressor. And what was that? Okay, it's LINREG, and we are predicting on this. We are computing these predictions here. Okay, we call it LINMSE, and we say LIN. Okay, and we then print. So we did the same thing with. Okay, what is wrong here? All right, I hope it is trained. Oh, it's actually the same thing that was done here. Okay, so we are basically predicting based on the housing data, and this is the value. So you can see clearly that when the linear regression model, it's basically not on 5 records. It's basically on the entire data set. The same thing has been done here. Whatever data we trained on, you see, we trained our linear regression model on the housing prepared, correct? By fit means we are training it. Okay, so you can see that the error in this case was 68,000 root mean square error, while the error was in this case 0. Same thing, exact same thing, right? The same thing done above here, above here. Is everybody clear so far what is that we're trying to do? No? So we tried to do, okay. So in case of linear regression model, the kind of error we're getting is this much for actual versus predicted. So in case of linear regression model, the the predictions are not exactly accurate. The prediction is off by 25%, and right. So root mean square error is this much. We have already computed. Now this model is clearly not great because the actual house values is between 120,000 and 265, and 68,000 error is not really very satisfying. Okay, so that's more like 50% error. Now this is an example of model underfitting the training data. Now, what is the solution to underfitting? The answer is select a more powerful model, feed better features to train algorithm. Okay, so what we do is we trained it with the dysentery. Dysenteries are capable of finding nonlinear relationship. This is a very good question. Again, people might ask you in case you want to, right? That can dysenteries take care of the complex nonlinear relationships? The answer is yes. Okay, answer is yes, and we'll know how later. Okay, we'll cover dysenteries in later in this course and understand how it basically predicts the nonlinear relationships. Now, going ahead, so here what we are doing is we are fitting the right? We've already done this part. So we did the dysentery fitting, and then we are predicting based on that. So here the outcome is 0. The output, the root mean square error 0, because we are predicting on the same data. Now this is overfitting. This is excessively overfitting because it kind of memorized every record in the input. Okay, so it's able to predict it. That's the reason why dysentery is actually known to consume a lot of memory and are Hughes model because they kind of memorize everything. Okay, so this is basically overfitting. And now what we're going to do is we are going to train on some part of data and test on some part. Okay, now we don't want to just jump onto the testing with the actual test data. No, we want to keep that final, the test data separate. And what we'll do is we will basically pick some part of the data and train on it. Okay, the best technique is to do the cross validation. So first you split the data into training and test. On the training data, we do the cross validation so that we could compare the models. Okay, a question from Manoj is, so it memorized in this case only, not in all cases. Why did it memorize? So it basically memorized in all the records in the, if you see, this is the housing prepared that we use for training. The housing prepared we use for training. Fit means when we are calling this fit, we are basically saying that please learn from this. This is our the all the columns and all the features, and this is the actual values. So this is the historical data that we are feeding it, and we are letting it learn from it. Now we are letting it predict here. We are saying that okay, this is our data and predicted. Now notice this, that this and this are same thing. So we are predicting on the training data, and the overall error is 0, right? Decent memorizes always, yes. If you do not constrain it, if you do not stop it, he'll basically memorize everything. Okay, you have to constrain it by saying that do not create a tree beyond this depth, or minimum of these many leaves should be there. Otherwise it'll going to just take the data, create a tree out of it, of the depth possible, and it behaves like a normal binary search tree. Okay, okay, so whenever we are going to ask a question, it's going to find out in the tree that which part, where in the tree this particular value exists, and it's going to just recall it. So it has basically organized the data into a tree, and when we are looking for a value, it's just going to that leaf and giving the actual value, whatever it was in the actual data, right? So that's what it is doing right now. Okay, so it won't be able to predict for the new output. Whenever you give it a new output, what it's going to do is it's going to go to a particular leaf and do the average of the values, and that's going to be really approximate. Now, question from Deepak is, after how many runs the algorithm can memorize the training data? It depends on the nature of individual algorithm. Okay, it depends on individual algorithms. Some algorithms don't really memorize anything. Okay, it all depends on that. Okay, so we're going to learn that part. We're going to learn how to fine tune an algorithm by hyperparameter optimization. Okay, Manoj was able to answer your question. Everyone, I hope everybody is on the same page so far. Feel free to ask in case I'm not, if in case you're not clear on something, because if you're not clear on something, chances are others are also not clear on something. Okay, right? So this is called overfitting, and we are going to use cross validation. Now, we should not touch the test set until we are confident about the model, until we are really confident about the model which we are going to use. We are not going to touch the test, okay? Because we'll again end up looking at the test data and tweaking our model, and we'll have nowhere else to go in case we do that, right? So what we're going to do is we are going to keep the test data is still test set is still separate, and still work on the training one, maybe further split that training into parts. Okay, so this is what we are going to use. We are going to use something called cross validation. In cross validation, what we do is we use part of the training set for training and part of the training set, remaining part of the training set as model validation. Okay, so this is what we are going to do. This was our original data set. We broke it down into training set and test set, and then we are going to divide the training set into two parts: a smaller training set and validation set for. Okay, so this is where we will let the models compete. We will let decision tree, linear regression, and other systems compete here. Okay, we will train it on this data, we'll test it on validation, and we'll compare. Once we are happy, once we see that, okay, this model seems to be doing good on our amongst other models, then we will go ahead with this. Okay, then we'll go ahead and test it on the final one. This we want to keep it till the end. We don't want to touch it now. This, when we test our model, that will be the end of the story. Okay, now the cross validation, the way we do is we break it down. We break it down. We what we do is we create, let's say, we call them folds. Okay, so we do say 10 iterations. In each iteration, what we do is we pick one part of the data that keep it for testing, remaining is for training. Okay, so we trained one model E1 on this. We trained the same same algorithm. We're using same algorithm. We trained another model E2. Then we trained E3, and so on. So basically, same data, different. I mean, different models are generated, and what we do is we finally take the average of all of these. We compute the error. Here we compute the error, and the error is basically this. So okay, so I think this E represents error here, not the model. Yeah. Yes. So on first iteration, okay, so what we did was we trained our model based on this, and we tested here. Then again, we basically trained on this as well as this and tested on this. Then a new model, the same algorithm we initialize again from the, and basically train on this, train on these parts, and test on this. This way, we are testing on unseen data, right, for the model, and we are training on this. Okay, and that's how we do that. Now, question is, how do we select the test fold? We basically shuffle this data and break it down into 10 parts, and that's how we basically create these folds. Okay. A question from Deepak is, how do we extract different test folds without repeating the same set of test folds? So all we do is we take the training set, shuffle it, okay, and then cut it into 10 parts, okay, and pick the first one, keep the last one once, then second one, and so on. We don't shuffle between these iterations. Okay, we shuffle bit before this iteration. All right, that's why we don't want to, the test fold appear here and so on. Okay, so idea is to, this technique is called cross validation. all we did was, okay, 10% of the data we keeping here, 90% of the data we are training with, and then testing against that one. And then we choose another piece, right? This one for testing and remaining for training, and that's all we keep on doing. Okay. And then the error that we get is the average of all of these errors that we got here, and that's what we're trying to do. So we reduce the training set by 10% here, which is completely okay to reduce the training set by 10%. That's right, Deepak. So we broke it down, we shuffle the data, we broke it down into 10 pieces and select different piece each time as the test fold for each iteration. So we could use scikit-learn's train test split function to split training set into smaller training set and validation set, and then train models against the smaller training set and evaluate them against validation sets. We could also write our own function. We could write a for loop after shuffling, and we keep on changing the window, right? But there is already a function called cross validation. So what we do is we call this cross val score. That's part of the model selection package of scikit-learn. So we are saying from this package, import cross val score. And there we are running cross val score function by providing our model. Do you see the model here? This is the model that we created. Right now, we have not trained it. We have just initialized this object. That's all. We have not called fit on it, right? And then we basically give it this data, the housing prepared, and the labels. Okay, and we're going to do the scoring here, and then we are saying that the folds are 10, right? The folds are 10, and now here we are saying that 3 RMSE scores equals NP dot square root of negative, right? Now, why are we doing that? Because as a thumb rule, okay, we will talk about it very soon. So here what we're trying to do is we are saying compute the cross validation score. What is the cross validation score? Error against each of the folds. And here the scoring mechanism, how do we score, is negative mean squared error. Okay, negative of mean squared error. That's the one that scoring we are going to use. And we are giving 10 folds, and here we are doing the square root, right? So since this scoring is going to be negative because right, because of the mechanism here, therefore we are going to put negative sign again and do that work, right? So here this is what we are doing. Yeah, so this is what we are doing here. And okay, so you can see that the mean error is around 71,000. The standard deviation is 24,000, 22458. Now this error is real error. Okay, this error is real error uh, because this one is not going to overfit. Okay, this is not based on overfitting. This is based on real error, right? Earlier it gave us 0, right, when we did the error, but this time the error is 71,000. Okay, this error is 71,000. Also, we have the computed the standard deviation. Okay, scoring is a measure of performance. That's right, Deepak. So yes, so what we did was we basically here we call this cross validation score, and it gave us the scores, and then we computed the average and we are displaying that. Okay, and then here we are doing the same thing. Now you can see that all we have to do now is we have to just call cross-validation score on all possible algorithms, right? All possible algorithms that we know of, and then we compare the result. Okay, so you can see that we're getting we're getting the mean error to around 69,000, while in case of decision tree, we got 71,000. So which one do you pick? Do you pick the linear regression or decision tree between these? The only difference is there is a minor difference in the standard deviation. Uh, standard deviation is around 2731, meaning the error is varying between the folds. Okay, little bit more than what it was varying in case of decision tree. Okay, now there is another algorithm. We're going to try that. So we have tried two algorithms. One is decision tree, and other is what? Other is the linear regression. So similarly, we are using the third algorithm called random forest regression. Okay, random forest regression. We passing the same random state to have the results in align with what we have shown previously. That's why we are fixing the seed, and then we are calling the fit just to do that. And finally, we are calling the we are it doesn't make sense to do all of this. We're just doing it manually. Instead, we'll just use the crosswell score. Okay, so let's take a look. So here it's going to break it down, break the data into so many parts, and it's going to train our model on that. It's taking some time because the random forest regressor takes a bit of time. So here the mean error is how much? 52,000, right? Earlier it was 69,000, right? So which one would you pick between the random forest and the other one? And also the standard deviation in the error is similar, is lower than the decent tree. So we got three models now. We got three models to compare. Okay, so you can see that linear regression, decision tree, and random forest. Okay, so decision tree is giving that error like 71,000. Linear regression is giving 69, but it has got a lot of variance. And decision tree is having low variance in the standard deviation. There's a less deviation from between the errors, and the random forest has better standard deviation, smaller, and mean is basically having a low mean error, right? So which one would you use? Probably random forest. The only downside of random forest was it took only a bit more time to compute, right? So random forest only took a little bit more time to do the computation. All right. Now, yes, that's right, Manoj. So random forest, you know what is random forest? Random forest are, very shallow decision trees, which have been ensembled together. Okay, that's what a random forest is. And you can see that by ensembling a bad performing model, you can actually do very good thing. Ensembling as in creating under the hood. Random forest might be creating maybe like thousands of decision trees and getting the results. Okay, so internally, random forest is creating like thousands of decision trees, asking training independently internally on different parts of the data, and then it's basically asking them for predictions when somebody asks random forest for the prediction. Okay, so you can see that the random forest can do a better job than the decision tree. It's like manager performing better than the team, right? So the manager can always take the bigger credit. Okay, so so that's the the ensemble models. So question from Deepak is, how many algorithms do we try? Quick answer is as many as possible. You should actually give it a try on this one. Another algorithm called XGBoost. It should be available. I'll just test it out. So XGBoost we had installed earlier in this lab. So XGBoost is the new algorithm that kind of keeps winning the contests. It's a different kind of ensemble. It's designed in a similar way like random forest. Okay. So all right. So yeah, thank you, Satyajit. So yes, H2 Fox must be talking because on Kaggle, the XG boost, extra gradient boost, is quite popular, and it seems to do a pretty good job. Okay, let me just check if I had already done it. I'd kept one example of XG boost somewhere. Okay, let me make a note to myself. Okay. All right, so let's take a break for 10 minutes and then we will fine tune the model. Okay, so random forest is definitely better. Okay, when you don't have any other choice of the models, then we ensemble. Otherwise, we just use off the shelf models. Okay, so we're going to shortlist the one. So we are done with exploring models right now. For now, we just explored 3 models. You should try more models and see the outcome. Now, a quick point to all of you, that whether you use Java, whether you use Python, PyTorch, or say scikit-learn or R, whether you use scikit-learn or R, or say any other machine learning tool, the the outcome will be the same. Okay, outcome will be the same because the implementations are going to be the same. So you won't get the better error or mean or standard deviation in say R. The errors and as well as the standard deviation will be the same. Okay. The only difference will be that in case you are using a faster computer, faster programming language, then probably this might take a less time to come up to. Okay, that's all that is the difference. Otherwise, there is no difference in the accuracy. Okay, as long as the models are same, the way they're written, they all are same, you will get the same output. Okay, now we will start with the fine tuning after the break. So let's take a break. So next is the fine tuning of the model. So once we have selected a model which is doing good, which is drastically, which is clearly the winner, what we do is we fine tune it. Okay, we fine tune it. Okay, and in this section we're going to do that, and it's okay if you don't understand the code because these parameters that we're going to fine tune, we do not know yet what are those parameters, just that we are going to do kind of blindfold way of trying, or you can say it's kind of hit and trial method. Okay, and it's completely so if you look at machine learning closely, it's essentially a combination of trying all possibilities as well as doing the mathematics, like the way we've always learned the things is to predict unknown things using maths, right? By drawing a straight line by various means, right? So the only difference with it is that that maths has been combined with the computing, whereby when we are not able to predict something using a formula, we use the iteration. We use the brute force. Brute force and iterations are generally used interchangeably and as the word. So what you're going to do is you're going to iterate over many things. When we don't understand many things, we just iterate over things. And that's a common way of doing things in computing. Okay, in computing, because that's the basic form of intelligence that we just iterate with everything, whatever gives us great results. Okay. Now we have 2 to 5 promising models. Let's fine tune them. Okay, how do we fine tune? So before learning about how to fine tune the models, let's learn about hyperparameters first. Okay, so what are the hyperparameters? Every machine learning model is more or less like a mathematical formula with number of parameters that need to be learned from the data, right? Now, the soul of machine learning is fitting a model to the data, right? By training a model with existing data, we fit the model parameters. Like when we are drawing the line has 2 parameters. One is the slope and other is how far is it from the center. Because there are many lines with the same slope, many parallel lines with the same slope. So um, the second parameter that defines the line is how far is it, right, from the center. Had it been in three dimensions, right? Had the line been drawn in 3 dimensions, it's called a plane. It's the plane is basically, you can think of an infinite sheet of paper floating in the 3 dimensions. So so in case of a plane, we have more such parameters, and as and when the dimensions grow, the simple linear regression becomes more and more complex to visualize, right? So basically, the number of parameters grow. So there are difference between parameters and hyperparameters. Parameters is these values, these these things that we have learned. That's the model parameters, right? In case of straight line, we learned where to draw the line. In case of a decision tree, we learned how to separate the data and so on. Those are the model parameters. Okay, those are the model parameters. Now there's something called hyperparameters. Every model provides us provides us knobs which we can configure. These are not easy to learn parameters. These parameters express higher level properties of the model, such as its complexity, how fast it should learn, and so on, right? These parameters called hyperparameters. These are the configuration of algorithms. Hyperparameters are usually decided before actual training begins. So we will basically configure these. These are like configured settings of an algorithm, which basically or a model which basically gives us the results. It can be decided by setting different values, meaning brute forcing, or and training different models and choosing the values that work the best, which we know the best. Okay, so people share these hyperparameters values with the world. If you take a look at the Kaggle, there'll be some winning settings of XGBoost and so on. So number of leaves, say for example, the examples of hyperparameters is number of leaves or depth of the tree, learning rate, how fast a model should learn, number of hidden layers in deep neural network, how many neurons should be there in the neural network, and number of clusters in k-means clustering. So these are the examples of hyperparameters. In case of linear regression, the hyperparameter is what should be the degree, as in should it be 2-degree equation that we are trying to fit, are we trying to fit a linear regression, and so on. So those are the hyperparameters of a model, right? So you'll learn how to fine tune the models. Okay. One of the solution is to fiddle with hyperparameters manually. until we find a great combination of hyperparameter values. Now, doing this manually is a very tedious task, right? And we may not have time to explore many combinations. So what we do is we use grid search. Now, grid search is an interesting concept. So we evaluate all possible combination of hyperparameter values using cross-validation. So what we do is we create we take the list of hyperparameters, and for each of the hyperparameters, we say that, okay, let its value change from here to there, and and we do that for all the parameters, and let the system generate all the combinations, all the permutations, and all the combinations, not permutation, all the combination of these parameters, and then call the cross validation under the hood and pick the one that's giving the minimum error. Okay, so we are going to do this, right? For example, in case this is our parameter grid, okay, it's going to provide these features to these hyperparameters, not features, these hyperparameters to this algorithm called forest, this model called forest regressor, right? So what's happening here is that we have imported the grid search, right? This is the grid search that we have imported. Now we define this parameter grid. Okay, parameter grid. It is an array. It is an array of dictionaries. Okay, this is a dictionary. This is another dictionary, and so on. Right. So what we are doing here is this is one combination. This is another. Okay. So what it's going to do is it's going to try our model first with these arguments, then with these arguments. Okay. So for each of the curly brackets, it represents a dictionary. So it's going to try our forest regressor with these parameters first, then these parameters first. Okay. You see number of estimators repeating here and max features repeating here. While bootstrap here, we did not provide. Okay. So this forest regressor takes many arguments. This forest regressor takes many arguments such as number of estimators, max features, bootstrap true or false, and so on. Right? This is the arguments. These are the arguments of forest regressor. When we do fit, we can, when we do forest regression initialization, when we do that, we could provide these features. We could provide these arguments, not features. These are the arguments that we provide here when we call fit or when we initialize it. Now here, what's happening here is that it's going to first, how many times it's going to call this forest regression? First, it will call on this, then it will call on this. Now here, there are three values to try for number of estimators, and there are four values to try for max features, right? So how much it would be? So this one will 3 into 2, this is 4, so 12 times this, and 3 into 2 into 1, which is how many permutations, how many combinations? It's 6. 6 plus 12, total 18 times our fit method is going to be called. Fit and predict. And based on that, further, if we are doing cross validation under the hood, is going to basically, since we are having 5 as the cross validation folds, right, it's going to call the cross validation under the hood, and there'll be 180. This is how much? 12 plus 6, 18, 18 into 5. So the algorithm is going to be called 90 times. Okay, the fit and predict is going to be called 90 times under the hood. 5 times for each for the cross validation, and and 18 times for this. Okay? All right. Let me explain to you. So there will be, okay, so here is the grid. All right. So what it does is, all it does is, it is going to go, let's say, for I in 3 to 10, like this. Okay. And for j in this to this. Okay. And it is printed. We are just printing right now. Just I'm trying to show you how many times it's going to try. So it's going to try a total of 18 times. Okay. So I'll just show you this part. And so here we are running the grid search. So these are the parameters of the grid search CV. It takes a parameter grid that we have prepared here. It's an array of dictionaries. This is one dictionary. This is another dictionary, right? Okay. These keys, these are algorithm specific. Okay. If you take a look at, say, here, right? I'll just show you. Okay. So you can see that this is our random forest regression. It takes these arguments. You see these arguments? These are the arguments that we have defined here. Okay. Instead of us, all right, let me just show you what's going to happen here. Okay. So, so under the hood, it's going to kind of call this random forest regressor with this equals 3, comma, max features equals max features equals to 2. This is what is going to happen, right? And it's going to say 4, then it's going to say 6. Okay, basically it's going to say now run crosswell score on this. Okay, this is what's happening under the hood. When we are running this grid search, this is what's happening under the hood. Okay, good. I'll just fix it. All right, so this is what's happening there. And we could do the same thing again, like 3 times. Okay, and here it's going to be 10, and here it's going to be 30, right? So you can see I'm talking about this. Okay, parameter grade. For parameter grade equivalent of this is, okay, first it's going to try number of estimators equals to 3, create random forest regressor, and then call cross validation score on that. Okay, then it's going to, for each of the second parameter, is going to do that. And then after that, once it's done with this, then it's going to call it on, it's going to call it on, I'll just put it this way. Right here, it's an extra parameter is passing. All right, I hope this is clear to all. Right, number of estimator is this, and so on. Okay, so this becomes 2, 3, 4. All right, and this is 10. Perfect. Is it clear? So it's going to call the Crosswell score on all of these, right? basically what is the crosswell score we're passing as how much? CV equals 5. So this argument again is going to be told to the crosswell score. How did we do earlier? By using, say, crosswell score, CV equals to 10. So here, everywhere, it's going to be that. It's going to be something like this. Crosswell score in the last will have CV equals 5. Is it clear? This is what is happening under the hood. Good. So this is what it means by this particular grid search. Okay. So in grid search, we are telling that try this. The all the values for this particular argument is going to be these. All the values for this argument is going to be these. And then in the second run, do this. Okay. So that's what is happening here. You can see. First, it's going to try. First, it's going to try number of estimated 3, then 10, then 30, 3, 10, 30, and then it's going to pick these ones and run. All right. Is it clear to all? I'll say Deepak, Jay, Manoj, Nikita, Prasant, Robert, Robin, and Satyajit. Okay. So instead of rewriting all of this, you must have realized by now how boring and tedious it is to just type it out. Even seeing me do it, you might be yawning by now. Okay, so here you can see the the labor. There's a lot of work involved. So somebody basically wrote a nice function called grid search CV and cross validation, so that you don't have to do this by yourself. Okay. Now, question from Deepak is, how do we choose different parameters? Now, how do we know on what basis can we we need to basically define these? On what basis do we basically define? We create these parameters. The quick answer is that we will discuss it later. And just think of it right now. We don't know. That's why we are just trying these things blindly. Okay. We don't know. That's why we are trying this blindly. And that's the truth. A lot of smart people you meet who talk about how successful they are at Kaggle, most of them, they had a random luck at these parameters for for various arguments. All right. Most of the time, it's a random luck they got with the arguments. But the truth is that people don't more even the researchers don't understand that what would lead to a great outcome, though we will understand what it means by each of these values and how it helps. But a number of times it's just a plain luck, so we leave that to the serendipity and try all possibilities. The question is, why 5, not why max features or number of estimators 3? Why not 3 million? Right? We, it could be anything. Now for that, we have the next nice method. Okay? We have a next nice method other than grid search. CV equals 5 means we are saying that cross-validation should break down the data, the training data into 5 parts. On 4 parts, it's going to try this particular predictor, right, for training and predicting, and on the the fifth part, it's going to test. So it's going to break down. This is basically the number of folds in the cross validation. All right. Moving ahead, so let's take a look. It's going to take quite some time. It's going to take around 18 into 5 and then run that combination again. So here we are saying, we are calling random forest regression. So we are chaining here the grid search is calling the cross validation is calling your actual algorithm. All right. So grid search is calling crossval internally, and that crossval is calling your algorithm finally. Okay, we are saying grid search dot best parameters are these. You see max features this, number of estimators are these, and the best estimator is okay. Also, the best parameters when we run grid search, it gives us something called best parameters. Best parameters are the parameters which gave us the best result. Okay, and who is the best estimator right now? The best estimator right now is the this particular one, random forest regressor, and these are the parameters. Okay, all right. Just to find out, what we can do is we could get the results and iterate over those and figure out the parameters of the result for that particular algorithm. So you can see that in here, this I think this is the one, right? Okay, is this the right one? Is this the one that is having? No, it's actually this one. 49494. Do you see anywhere 4? No. So it looks like this one is the one that has the best outcome. So max features has 8, number of estimators 30, is giving us 49,694 error, mean square error, root mean square error. Okay, so that's the grid search. Grid search essentially lets us basically define an array of values for each of the parameters for your model and let it run. Okay. Now, the second part is the question from Deepak is, what is the percentage of error we achieved? It's a hard thing to do because when we say percentage, it's not possible to define percentage here because percentage will be something will be in the denominator, right? And if we sum it up, that's what we get out of after squaring it, that's what we get here. That's why the percentage error is actually hard to define, right? So the mean error is basically, you can quickly estimate that if the house value is this much and we are getting this much, that means we are doing pretty good. Okay, so we'll talk about the error again. So percentage error is a little harder to define in these cases. The best is to just stick with the root mean square or root mean square, because root mean square represents the error in individual house prediction, right? Because it's average of all the values after summation. Now, a number of times we don't know what are the parameter values, right? Sometimes it could be a million or sometimes it could be in decimal numbers. Therefore, we don't know exact values. So for those kind of reasons, what we use is we use the randomized search. The grid search approach is fine when we are exploring the relatively few combinations, right? When the hyperparameter space, such space is really large, then we use the randomized search CV rather than grid CV. We'll cover the randomized search in grid details. So randomized search, instead of trying out all possible combinations, we evaluate a given number of random combinations. So what we do is since you just saw that as the permutations rise, the total number of iterations keep on getting multiplied, right? As the number of parameters or the values rise, let's say we want to try something between 1 to 1 million, right? It could be 100, 10,000, 50,000, and so on. There could be like thousands of values. So instead of trying all combinations, what we do is we let it just pick random combination by selecting a random value for each hyperparameter at every iteration. And we can just fix the number of iterations that we want to run. So say our randomized search runs for 1,000 iterations. It will explore 1,000 different values for each hyperparameters, while gradient search explores few values per hyperparameters. The randomized search could actually explore far more values. Okay, so it has more control over computing budget you want to allocate for hyperparameter research, and we can just set the number of iterations. Okay, so here we have, you can see it's pretty straightforward. All we have to do is define the parameter like this, right? Also, please notice that there is here, okay? So there is, we are saying that give the random int between 1 to 200, okay? Give the random integer between 1 to 8, and the random state is 42, okay? This is not really hyperparameter, it's just we fixing the seed. And then what we're doing is so here what we're doing is we are taking this, the model, giving the parameter distributions, and this is how you define the distribution. Any integer between 1 to 200, any integer between 8, like that we have defined the values, and then we are passing this parameter distribution to our algorithm here. And then we are passing these arguments. We are saying only try 10 iterations, not more than 10. And the cross validation number of folds we have defined here. Then the scoring method is generally the negative of mean square error, because we want to decrease the error. Mean square error, the more it is, the worse it is going to go. And it should be as less as possible. Okay. So that's why we use negative mean square error, and then we do the fit. Okay, let's do that. Okay, a question from Deepak is that, people ask about accuracy of predictions achieved. All right, so the accuracy of predictions generally is valid when we are doing classification. Okay, so how do we answer them? Okay, so what we can do is, okay, let me show you. What it means generally is, I'm going back, really back. Okay, yeah. Okay, let me go back here. Yeah. So you see, this is the way we generally give the accuracy traditionally. That this is our predicted, this is our actual. We subtract the two and then divide by the actual, right? That's how we define the accuracy. Correct? So here the thing is that we have only singular values, therefore we are able to report percentage error, and okay, and maybe we can take the mod and compute the mean error, as in the absolute mean error. That should also be okay. Okay, if somebody is really insisting on getting the percentage error, in that case, remove the sign from the negatives, and compute the average. That could be another way of reporting the error. All right. Now, there are very good questions. A question from Prashant is, in this example, how do we know that random forest was the best model? Maybe linear regressor could have given us better results after fine tuning. Good question. But in case of linear regressor, there is nothing much to fine tune, And but we could give it a try. You should give it a try and see. You should give it a try and see if it's able to give you good results. Okay, but it's a very good question that maybe after fine tuning, the linear regressor could have given us far better results, right? But you can see that after all of this fine tuning, the results have improved a bit, not huge, right? So so from our hunch, we realize that we may not get the linear regression to this level, but you should give it a try and let it settle down properly. That maybe the argument the various argument search is not going to give you better results. Various hyperparameters. Okay, so I think the best answer is just give it a try. All right. Most of it is based on the hunch because we know that random forest performs far better than linear regression and so on, but you should give it a try. Okay. The other thing that we keep on missing is that if you have like two best competing models, before we started doing grid search on the cross validation, we find that there are two or three very good algorithms which are equivalent in their accuracy and in their error. I mean, which have the minimum error. Now, okay, so another way of fine tuning is to we basically take those best performing models and combine them together, create an ensemble and get the results. So scikit-learn provides you ensembling multiple models in a very simple way. Okay, so random forests perform better than individual listening trees, and we did not go ahead with ensembling ourselves. But as we'll study further, we could, in case we are say trying 5 different algorithms or 10 different algorithms, we get, let's say, 3 best performing models. Now, what we can do is we can ensemble them together and let them perform. Okay, we can ensemble them together, let them perform together. Okay, so analyzing the best models and their errors. Okay, so let's see the importance of score of each attribute, right? One of the things that we need to do is at the end of machine learning, if everything is going good, then in the end, we need to find out the feature importances, right? So here, the way we can do is we can get the best estimator or best model, and from that we can find out which features have played the best role. So here it shows that here we are, this is how we get the feature importances. Okay. Okay, you can see that finally, after combining the parameters and so on, what we get is this. Okay. So you can see that this one is the most important feature, the median income, then inland, whether a property is in the land or not. Okay. Because we had converted all these columns into the categories that were not encoding that particular, right? And then we have the popular per household, population per household, then longitude, then latitude, then rooms per household, and so on. So once the model has been trained, the model has been trained and we have figured out this is the model, then we can also figure out a better feature importance, right? Remember, we did that correlation matrix. More than that, the feature importances play far better role. Okay, that just gave us a very brief overview of our data set, but the, the correlation matrix is not as good as the feature importances. Okay, so feature importance is far more better as compared to the any other mechanism. So once we have trained the model, we can even extract the feature importances. Okay, so you can see that after longitude and latitude, the accuracy seems to be good. All right. Now, once the model has been trained and we are convinced that this is the best we could do, after grid search, after doing cross validation, we realized that everything is like perfect as compared to other algorithm. We figured out our best model. So all we need to do is we test we test the model on the test set. After tweaking the model for a while, when we are confident about the model, then evaluate the model on the test set. Okay, the process is get the final model, right? So from the grade search, we get the best estimator, and okay, so we got the best estimator, and then we dropped a particular column. So here we are dropping the median house value. That's the one that we are going to predict. Therefore, we are removing that. So we're copying the label somewhere, and that's actually final data. So now we are transforming the test. Okay, we are transforming the test data using the same pipeline with which we have cleaned up our normal data. So our training data, this is the pipeline using which we did that. Now you understand the value of pipeline because we have used it multiple times, and here we are using the same pipeline for the test as well. Now once that is done, we do the prediction. We say predict on the test prepared and the report the RMSE. Okay, so on the test, the root mean square error that we got is around 47,766. Okay, that's not very bad because we had a similar score on our training data, right? So we have trained and tested our first model, and I hope everybody is clear about it. Now, till this point, whatever we have learned can be utilized for almost everything that is there in regression. This is supervised regression problem. If you are going for supervised classification problem, instead of mean square error, it'll be precision or accuracy. And it should not be a very difficult thing for actually solving the classification problems right away. Okay, so my suggestion to all of you would be in this class that give it a try to various models, the various challenges that are there in CloudxLab's my course. Okay, give it a try to them. There's a ride sharing one. Don't look at the solution, just solve it in your own way. Okay, solve it in your own way, because there we try to do multiple things. And few things I want to cover before we go ahead. There are a few things that are not included in this. Number one, what to do with the arguments like hour of the day. So although we had covered earlier this part, but again, it's a very common question that people might ask you. If let's say there is a data set called ride sharing. Have you seen that data set called ride sharing, right? So in which it's I think next project in this, if you go to the machine learning my course, there you will see that there is a column called R, meaning what is the demand of rides, cycles or bicycles or bikes, right? So there is a particular project which basically talk about predicting the bikes in a city. I'm not showing it right now. I'm just talking. So so in that problem of bike ride sharing or bike demand prediction, what we have to do is figure out, given the condition of the day and the time of the day, we need to predict the demand for the bike. So based on the geography, in which area, and what time, what date, we have to come up with. Now, based on that demand only, we will basically distribute the bikes so that people can rent the bike and take the bikes on the rental. Now, in that question, there is a column called hour of the day, right? Value of the hour goes from 0 to 24. Okay, the value of the one of the particular columns called R, it's the value it's going from 0 to 23, right? Not 0 to 24, right? Now, what is wrong with that? Do you find anything wrong with that column? Yeah. So you can see here that here there is a column called R. Its value changes from uh, from 0 to 23. See the value changing from 0 to 23. Correct? Do you find it wrong? Do you want to do something about it? It's not time series because we are not predicting time. We are just predicting normal. It's a normal regression. We're going to predict CNT, the counts of the bike in the demand. At this hour, this was the bike demand. Okay, this was the wind speed, this was the atmosphere, this was the temperature, and so on. So based on that, we're trying to predict the, okay, Manoj's point is that time zone issue. Not really, not really. Let's say that the time is in UTC. Yeah. Anybody else? Good point. So please go ahead. Yeah. Anybody else? So there's a column called R. So it'll go from 0 to 23. You see, it's going from 0 to 23, and then again starting back from 0 to 23. Okay. And if I say, okay, can I, what's the name? Like that. Okay, so almost like that. Yes? All right, I'll clear it. So the important part about this is that what is the distance between 0 and 23? Yes? What is the distance between 0 and 23? Not really. Not really. It's actually could be 0 hours or could be 24 hours, right? Therefore, the R is not a great predictor because what will happen is for somewhere the behavior of the bikes at 12,001 will be similar to the 12,000 as in 12 a.m. is similar to 11:59 p.m. right? So 0 and 23 are actually very close, right? Are actually very close. So 0 and 23:59 are going to be the same thing. While here, our algorithm, because algorithm looks at the numbers and would think that, okay, the 0 and 23 are far away and it'll get confused, correct? So how do we generally resolve such kind of problems? Are you with me so far? So how do we resolve such kind of problems when your one particular column, it's basically going up and then it's coming down? So a general thumb rule in such cases is to break it down into categories. We say this is morning, this is evening, this is night, and that gives a better prediction, right? That gives a better prediction. So we basically break it down into those larger buckets. Okay, although there are other mechanisms like mathematical ways of converting these values into instead of periodic, we convert them into increasing value, and that helps in many ways. So my strong suggestion here would be that we basically break it down into smaller buckets and do the rest of it on those buckets. Okay, so we convert it into morning, evening, afternoon, night, and so on. All right, so we are doing the opposite. We are converting a numeric value into categorical values. Okay, so we'll be converting it to numeric from numeric to categorical, and from categorical to one hot encoding, and that will give us better prediction. All right. Okay, this is based on a real interview from one of our learners. Basically, the one of the data science companies he appeared for, this was asked to him. That's why I thought that those who are planning to start their career journey interviewing, they can start doing it right away with this much knowledge. And also, when you are solving Kaggle kind of questions, you might face these kind of questions. All right, is everybody okay with that so far? So we basically, in such case where there is a repetition or circular thing, there it's generally better to break it down into smaller categories where the behavior of people is same, behavior of demand is same, and so on. All right, so we have trained and tested a model. This is not a perfect model though, but we'll learn more ways to make it better. We will learn to fine tune it as we go ahead. All right. If we do a lot of hyperparameter tunings, then the performance of the model will be worse than the performance measured in cross validation. This happens because the model is fine-tuned to perform well on validation data and performs badly on unknown data. This is another important part. Sometimes we basically kind of fine-tune it just too much that it becomes specific to the validation data. So hyperparameter tuning does not give you magnitude of improvements, okay? It does not give you the magnitude of importance, magnitude of improvements, and so on, okay? So we must resist the temptation to tweak hyperparameters to look good on the test set, okay? As the model must generalize well, right? And such models which is so much tweaked to fit to the test data is equivalent of overfitting. Will be basically overfitting and may not give the great outcome. Now is the pre-launch phase. Once you have come up with the model, please note that the prediction of the model takes far less time than the training, and we can launch this model, and we can basically we are ready to launch such model, and prediction takes generally fraction of time and as compared to the training. All right, so that's a small bit to know. Once we are done with it, we need to present our solution, basically what we have learned, what worked and what did not work, what assumptions were made, what are the model's limitations. Okay, now we have learned to present the solution. One of the things is document everything, create nice presentations, use matplotlib to plot the graphs whenever needed. And one of the things that you should display is one, the performance of your model in terms of mean square error or whatever performance you are doing, along with the standard deviation. And you should always list down the priorities of parameters in your data, right? So once you're done with presenting the solution, you should launch the system. Prepare the solution for the production, plugging the production inputs, data sources, and then once you have launched it, you will have to monitor it. So so this is another important part. So model slide performance need to be checked at regular intervals. So you will have to write the monitoring code. So if the model's performance is going below certain value, you should basically trigger an alarm, and this is important to catch the performance degradation as the model tends to rot. Okay, so imagine that you have trained a model to detect the spam or not a spam, and you upload it to a server. The moment the performance drops below certain value, just from time to time, you must keep on checking it on the data provided to you. You should trigger an alarm if the performance is going below certain value, right? So as the model tends to rot after a certain period of time, if you do not train it with fresh data, the model become rotten. Okay. Now sample the models predictions and evaluate them from time to time. This generally requires human analysis. These analysis may be done by the the field experts or workers on a crowdsourcing platform. Okay, so from time to time, you need to keep checking the outcome of your model. You can either hire the field experts or hire the people from the crowdsourcing platform, or basically delegate the tasks to the crowdsourcing platforms such as Amazon Mechanical Turk and Crowdflower, and there are quite a few similar systems. Okay, so similar platform whereby you can post these. Even people use freelancer for the same thing. So evaluate the model's input data quality from time to time. Performance may degrade if the input data quality is not good. For example, there is a malfunctioning sensors sending random values, then the model's performance might drop down. So monitoring input data quality is especially important for online systems and so on. Then you have to maintain the model, automate the process to regularly updating the training model. Otherwise, system's performance may fluctuate severely over the time. Make sure to save a snapshot of its state at regular intervals so that we can easily roll back to a previously working state. So this is what we learned. This is what we did in terms of cleaning the data, and then we yes, Deepak, that's right. The fresh data may have changed. Do we need to retrain the model? Yes, of course. In case your training model has training data changed, update the model and so on. That's why machine learning becomes a continuous process. All right? Yes, it's basically recalibrating the model. Okay? So automate the process of regularly updating the training model with the fresh data. Okay? But this is essentially what is called as, you can say it, recalibrating. Not recalibrating, basically rebuilding the model. And when you are rebuilding the model, of course, you are going to recalibrate. Okay. And similarly, from time to time, probably every day or so, you must keep on checking if it's giving the proper results or not. A question from Manoj. Linear regression gives predictions based on one line, and random forest does ensemble and gives prediction based on multiple lines. So random forest basically is based on the decision trees, many decision trees it creates internally. And the way it creates is it divides data into two buckets, and based on certain parameters, it picks up one parameter. And for each decision tree, it picks up different parameters on which it divides the data. And then when you ask a question, it is going to pick those buckets and give you the average of those. Yeah, I'm going to go more and more details about that. So you can think of ensemble as the, yeah. So random forest was the ensemble one, that was correct. And okay, but random forest specifically is an ensemble of decision trees. Okay, it's not a the ensemble of the regression, but but so it's not plotting that straight line the way we were plotting. Instead, it's using completely different logic. Okay, the decision tree is using a complete different logic. It's not based on linear regression, but we can ensemble multiple linear regression mechanisms, or you can say that by subsampling the data set, we could actually do that. The example that I was taking where we drew so many lines, just to give you an example that ensemble learning can be applied even on linear regression in this manner. Okay, I hope I did not confuse you guys. So random forest is an ensemble, but it's a ensemble of decision trees. Okay, while linear regression is not an ensemble, it's just basically the actual model. So this is what we learned. We did data preparation, deploying, building monitoring tools, setting up human pipelines, and so on. Get comfortable with the overall process. Know 3 or 4 algorithms rather than to spend all your time exploring advanced algorithms because, right? So spend enough time on overall process. We learned all of these parts in this chapter. Okay. I look forward to see you tomorrow. Bye bye. Have a good day.